A first-order differential equation is called homogeneous if it can be put in this form m dx plus n dy equals 0, with m and n both homogeneous functions of the same order. And we've discussed kind of what the characteristics are to look for, but let me just remind you kind of what it means for those functions to be homogeneous. When you replace the x and the y with a tx, ty, what you get is a power of t factors out, leaving just that function m. And then similarly, when you substitute in tx and ty for x and y respectively in n, you also get that same power of t to factor out, so they both have to be homogeneous of that same order alpha. And I'm not going to go too much into the details here, so instead I would suggest referencing kind of our class notes. But if you do have a homogeneous differential equation, to solve, we use a substitution. And our substitution is going to be one of two things. We use either y equals ux or x equals vy. Both of these substitutions are guaranteed to work, but the intuition is whichever function is simpler to work with, the m versus the n, that should kind of guide the substitution. If the quantity with the dx is simpler, use the x substitution. If the quantity with the dy is simpler, use the y substitution. Either way though, the dy is going to become u dx plus x du, just think product rule, or if you use the x substitution, dx is going to become v dy plus y dv. And the guarantee is that with this substitution, it reduces the differential equation to be separable, i.e. easier for us to solve. Once you have it reduced down to a separable differential equation, solve, and then don't forget to re-substitute. Let's go ahead and look at a very common example. To solve the given differential equation, I will note that it is also Bernoulli, but it turns out that this is also an example of homogeneous. So let's put it in that m dx plus n dy form. So the first thing I'm going to do is kind of just cross multiply here. We could write this as x squared dy is equal to y squared plus yx quantity times dx. And then I need to group these together all on the same side. So if we bring everything over to the left, we would have minus y squared plus yx dx plus x squared dy equals 0. And what I want to note is that for this function paired up with the dx and the function paired up with the dy, every individual term is made up of a polynomial of degree 2. So y squared, power 2, y times x has kind of that net power of 2. So this will be homogeneous of order 2. Same thing here, x squared is homogeneous of order 2. So both the m and the n are homogeneous functions of the same order, in this case 2. And what that tells us is that we have a homogeneous differential equation. And with a homogeneous differential equation, we can solve this using a substitution. So either y equals ux or x equals vy. And I'll also note that as long as you are sure that the functions you're dealing with here are homogeneous of order 2, you don't need to verify that for me. But just note that if this did not happen to be a homogeneous differential equation, the given substitution would not be guaranteed to help us solve it. So we do want to be certain. Now, when it comes to deciding on the substitution, the dy term is simpler, so I'm going to use the y substitution. So that would make dy u dx plus x du. And what I now need to do is substitute that in so that we end up with a differential equation only involving the variables x and u. So working my way from left to right. the y becomes ux. So I would have u squared x squared plus ux squared all times dx plus x squared times dy. dy is u dx plus x du. And this is very common. We make the substitution, and then what results kind of looks like a mess. But what we are guaranteed is that for a homogeneous differential equation, this substitution makes it a separable equation. So with that in mind, we just go with it. So expand everything out, see what terms combine or cancel, and then separate. So in this case, I'm going to go ahead and just do the distribution that we see. So distribute the dx through, and then distribute the x squared through that second term. That would give us a minus u squared x squared dx minus ux squared dx plus ux squared dx, that looks good, plus x cubed du, all equals 0. The part that looked good there in the middle is the two terms that cancel with each other. Now we can more clearly see it's separable. A term involving the dx, a term involving the du. Let's put the one with the negative sign over to the right. So we can make this be x cubed du on the left, add u squared x squared dx to both sides. Now separate. So divide both sides by x cubed, divide both sides by u squared. And once it's separated, we solve it as a separable differential equation. So that is to say we need to anti-differentiate both sides. On the left we have minus 1 over u. On the right, natural log absolute value of x. And we need to get that plus c in there. And after doing all of this wonderful work, make sure to finish the problem up correctly. We always finish a substitution with a resubstitution. So looking above, we see that y equals ux. So that tells us that u needs to be replaced with a y over x. So if u is y over x, we would have minus x over y, the reciprocal of u, equals natural log absolute value of x plus c. And this is the solution of the homogeneous differential equation.